Okay. So in this lecture, we are going to talk about living crystals. Living crystals is something that scientists observe in a microscopic environment where they have microswimmers swimming inside a liquid medium. And what happens is that they bump against each other and kind of get blocked by each other and create this kind of crystal structure by microscopic particles inside the liquid environment, which we will see some experimental videos in the slides. And this image you see here is a picture of an old, I guess, Greek god that its name is Janus. It means that two-faced god. And this refers to some of the configuration of the microscopic microswimmers that are artificially made, that people actually coated asymmetrically some microscopic particles and make them kind of be able to propagate inside the liquid environment. And we will talk about this kind of particles in this lecture. So let me try to, yeah. So no. Okay. So what is a Brownian particle that we have seen in the previous lectures, right? Quite a few examples. In this case, we consider two dimensions because it's for this particular case the easiest to kind of interpret or comprehend. And in two dimensions, we have just, if we have only a Brownian particle, we have just diffusion along x and y, right? Which is proportional to a, let's say, diffusion coefficient that I denote here with dt. T there relates to, means that it's translational diffusion coefficient. That's because we are going to introduce another diffusion coefficient very soon. So if you have an active particle, it means that this particle is going to propagate inside the liquid environment. It won't only move by the random forces that are happening because of the collisions from the motor molecules, but it will also be able to propel itself in a certain direction. So exert power on itself, right? Like we are doing inside the swimming pool, right? We can kind of push the water molecules back in order to go forward. Microswimmers can also do the same in some kind of symmetry breaking inside the liquid environment. In that case, their equations of motions will be updated like this. So whenever they have an orientation phi and they're going with a velocity v, their differential equations that are governing their motion in x and y will change like this, right? So they will also move in x with a constant velocity. However, we also need to understand this, how this is going to change, right? How their orientation is going to change. Because in a macroscopic environment, if I'm swimming in a certain direction in a swimming pool, I will go forever in the same direction, right? If I intend to go on this way, I can do it, right? Microscopic particles just can't, because just like the regular diffusion, they are also subject to rotational diffusion. This is because the random collisions between motor molecules and a microscopic particle doesn't only apply a random force on the particle, but it also applies a random torque at a time. So they are not able to conserve their orientation all the time in the same direction. What happens is that their orientation is also diffusing with a random kind of diffusive motion, which we denote the strength or the extent of this diffusion is here denoted by this dr, which is the rotational diffusion coefficient. Larger the particle radius, this rotational diffusion coefficient dramatically is reduced. For example, the regular diffusion coefficient is scaling with 1 divided by r. The rotational diffusion coefficient is scaling 1 divided by r to power 3. When the particle is getting 2 times smaller, its rotational diffusion is increasing by 8 times. So that's why we don't really see it with even like slightly big particles, 10 microns, 20 microns, really, like they're still microscopic, but slightly bigger than smaller particles. The rotational diffusion is dramatically reduced. But as the particles get smaller, this is really becoming overwhelmingly big, this rotational diffusion. That's why it's incredibly difficult to artificially generate nanoscopic swimmers, nanoparticles that go in a certain direction, because their rotational diffusion is incredibly large, that their orientation becomes uncorrelated with itself in a few kind of milliseconds. So these are how these diffusion coefficient scales. Both, of course, is proportional to with the temperature, because the higher the temperature is, which means that there is more kinetic energy in the environment from the collisions with the water molecules. There is more energy coming that can kind of change the particle orientation or place. I will just close this window. Maybe here. Okay. So if these are typical example trajectories of the microswimmer that are going 3 micrometer per second, but it's not maybe it doesn't really mean much. But sometimes we also have a kind of tendency on a microswimmer that is not only changing its orientation randomly, but it's kind of have a chirality. That is, the particles kind of maybe asymmetric in some way. As it is propelling itself, it's kind of applying a certain torque. You can think of this as a car that is not very well balanced, so that if you just let the direction wheel itself, it will not go straight, but kind of tend to go one direction or the other over time. So microswimmers can also be like this sometimes because of the broken symmetry in their configuration. This results in a motion that is chiral, that looks like this. So they propel itself, but they cannot do it in a straight way. So they kind of turn right over time, or they can also turn left. This is an example of course, here we show an example with very high velocity so that the rotational diffusion effects are smaller, so that we can actually see the chirality. If the velocity is much smaller, maybe it's not as easy to see this kind of chiral trajectories. Is this clear so far? Yes? Okay. So these are the equations of motion, right? And here we also, as I introduced in the Brownian motion lecture, if you remember, we have to rescale in order for my simulations to be independent from my choice of delta t. I need to rescale the noise terms, and I have to kind of pick individual noises. That is important, that when I take a random number, when I'm simulating these, they need to be independently generated, each component. So X component, Y component, and the angle. If not, they will be driven with the same random number. That won't be accurate for the simulations. So this is the corresponding difference equations, right? Just like the one in Brownian motion lecture, what we have additionally here is a term that is a swimming term here in X and Y difference equation. And we have over here a chirality term. This might be 0 often if the particle is not chiral. And I also have a rotational diffusion term here. So instead of updating X and Y at a time with the velocity, which is also actually related to the orientation of the particle, we also update the angle every time step so that it is changing slightly due to the rotational diffusion. And these are the exact difference equations we are going to apply when we update this particle, if we are talking about the single microswimmer motion. Is this clear? This is a motion of a particle that is not interacting with anything else but the liquid molecules around itself. Sorry? This omega chirality. So that is the thing, that is if the particle tends to go kind of turn right or left as it is propelling itself. And this might be 0 often for a regular microswimmer if it doesn't have a chirality. Okay. And here I'll show you a few examples of microswimmers. Here you see particles with no chirality. They just go in a certain direction, swim, and then they are subject to rotational diffusion. Of course, when we have a velocity, swimming velocity that is 0, which is the red particle here, you see that it's doing purely Brownian motion. And then as I increase the velocity, you see that the motion of the particles become more and more like consistent in one direction than the other. So it's becoming less random. And their mean square displacement is now showing a super diffusive behavior, which we talked about in the anomalous diffusion lecture, if you remember that. So this is my regular diffusion slope, which belongs to this particle that doesn't actually swim. Its swimming velocity is 0. In that case, its mean square displacement is just linearly increasing with time. However, when I have a micro swimmer, while its swimming velocity is constant, its mean square displacement is scaling with the square of the time elapsed. Because if I'm going in one direction, swimming or driving a car or walking, whatever, without changing my direction, I lose the randomness, right, in short time scale. When I lose the randomness, my square displacement is increasing with v squared t squared, because my displacement becomes kind of v times t. I'm talking about the scaling here. And my square displacement is kind of scaling with t squared. However, when I am looking at a system in very long time scales, what will happen is that eventually all of these particles, even if they have a swimming ability, their orientation will be uncorrelated with itself. If we compare a while ago and now, if there is enough time has passed, what will happen is that the particle will be swimming in a totally different direction than what it was before, right? So these motion, all of these motion in a very long time scale will go back to some kind of enhanced random motion with kind of an effective higher diffusion coefficient. And you see here that if you look at the system in long time scales, what will happen is that the ones that move with a swimming velocity, their mean square displacement also scales similarly with slope 1 at the end of this plot, but kind of with an enhanced amount, right? They diffuse, of course, more, but their diffusion kind of goes back to random. If we look at a system in a very long time scale perspective, is this clear? Of course, in short time scales, it doesn't look random. It looks like they go in one direction. But since they have rotational diffusion, this is very important. So they will eventually turn another way and another way and another way. In a very long time scale, their motion will still look random. If we take this trajectory and take it for a much longer time and zoom out, look at the whole trajectory, it will look very similar to this. Is this clear? So it's important, how are we looking? At what time scale we are looking into the motion of these particles, or length scale similarly. Okay, now we kind of understand the model, the fundamental model, how we kind of mathematically formulate the motion of these particles. We can kind of look at the examples, how actually these particles can be found, right? First, they can be naturally found in nature, right? Bacteria, they are kind of able to propel itself in a certain environment, right? And these are like bacteria that are swimming smoothly in a microscopic environment, right? And what happens is you can ignore this particle that is a microscopic silica particle. But the rest of the bacteria you see here are quite motile and moving right and left quite randomly in one direction they see. Of course, these bacteria are also subject to rotational diffusion because they cannot actually conserve their orientation. And as they swim in one direction, eventually they will turn. What they do is that practically, in order to navigate inside the liquid environment, is that they tune their swimming velocity. If they are going in a direction that they don't want to go, what they do is they slow down and wait until the water molecules kind of their orientation turned on the other way, and then they kind of start moving again. And also there is another kind of swimming behavior, which is called run and tumble swimmers. These bacteria are kind of swim in one direction, bundle their flagella, and then once they kind of, after a while, what they do is, in order to reorient, they kind of relax the bundled flagella, kind of reform that again, so it kind of formed in another direction, so they kind of start swimming in another direction. Of course, these are natural ways that we can observe microswimmers in microscopic environments, but how can we actually generate them? If we want to model or do experiments or artificially create microscopic microswimmers that can actually do something for us in an environment, in a biological environment, for example. How can we generate this particle? The most, one of the first way people thought of is this following particle that we actually named Janus particle. It takes the name from the god that means the two-faced god, because it has two faces. What people did was that they took a microscopic sphere, which is made of silica, and then they coat one side with gold. And it looks like this if you take a microscopic image of these particles. Of course, this is not super accurate, but they kind of roughly spray or either coat one side with gold. And then what happens is that I can actually shine laser light on this particle. What happens is that, for example, green laser light is very much absorbed by gold. What happens if in that case is that the gold side of the particle becomes very hot. What does it mean? It is creating an asymmetry of the temperature around the particle, right? Which means that it's creating a big asymmetry of the collisions by the water molecules on the particle. From one side, the water molecules will collide more than the other side due to the increased temperature. And also when they collide, they kind of transfer more momentum or more force. This creates an asymmetry on the particle that the particle moves in kind of one direction in a microscopic environment. Is this clear how the fundamental idea here works? And also there is another chemical way people have done is that it's a similar kind of way that we have a particle that is kind of cylindrical and half of the particle is coated by gold and half of the particle is coated by platinum. And this is kind of something, we have a environment that is hydrogen peroxide rich. And what happens is that this platinum side is kind of getting chemically activated, reacting with the hydrogen peroxide and creating a chemical reaction on one side of the particle, which is kind of creating these kind of bubbles, because you see that this is releasing, converting hydrogen peroxide into water and oxygen. What does this mean? Oxygen is gas, right? So it's creating bubbles on one side of the particle. It's kind of working like a mini rocket in a liquid environment, right? Of course, this is kind of I don't know, in my opinion at least, a little bit more novel. Why? Because you can control it externally. It works with light. This, once you put them in the environment, if there is hydrogen peroxide inside liquid, they will move forever. You cannot control the motion. And what is worse is that once the liquid there is no hydrogen peroxide left in the liquid, they will stop moving. They're kind of running kind of on a fuel. And of course, people have done kind of some ways that mimic the motion of the bacteria. Here you see that a small bead is attached with a magnetic tail. And then what they do is that they control the motion of the tail with an external magnetic field, which makes it rotate kind of a flagella of bacteria, and then makes this particle be able to propel itself. Here is another way of this kind of model, but working with a spherical particle instead of a cylinder. You see this very small particle. If you can't see it from the slide, maybe the resolution is not good enough. You can actually look later on YouTube. There is a tiny particle here that is propelling itself here and there. And of course, another way is the creating kind of a, this is a last example, how we can realize it's the same kind of working principle as this one. We have a Janus particle that's half coated gold, but now we have a critical mixture, which is kind of a, you remember the lecture of icing model. Sometimes liquids are kind of resolved within each other under a certain temperature and get kind of separated, phase separated above a certain temperature. What happens is that if I take such a critical temperature and place it very close to critical temperature, what happens is that any kind of increase in temperature creates very large phase fluctuations in the liquid, which creates a lot stronger asymmetry than this one. It's kind of working in a similar kind of behavior, but these particles move a lot faster than these ones. Okay, some kind of way to amplify the ability for the microscopic particle to be able to propel itself. Is this clear so far? And also we can, of course, make different kind of microswimmers. For example, I mentioned chirality, right? As a particle is swimming in one direction, it can kind of turn in one way or another. People can also do this by kind of like the same way we create a motion, kind of a propelling mechanism. We coat one side of these L particles from below, and when we shine laser on it, what happens is that they propel themselves. What happens is that this is kind of turning in one way as it's propelling itself because of the asymmetry of the particle, because the friction doesn't apply the particle symmetrically as it's propelling itself, because it's asymmetrically shaped. Depending on how the particle is shaped, or kind of if actually they're the same particles, but they happen to be like if this falls on this face, it is like this. When you put them in a microscopic environment, they are the same particles. But if it falls in the microscopic environment on its the other face, it's kind of becoming like this. They are kind of sitting on a two-dimensional glass slide at the end. And then, of course, they kind of not only propel itself, but also kind of are able to rotate. Okay. Is this clear so far? Okay, now I will quickly describe what is the fundamental difference between microswimmers and standard Brownian particles. The fundamental difference is that when we talk about standard Brownian particles in a thermal environment, they can kind of reach equilibrium. It is trivial to guess what is their kind of distribution is going to be. Even if they are not in a flat environment, they might be like kind of trapped in an environment. For example, this kind of optically trapped Brownian particle that is trapped with a laser. What I can do is, if I know the potential that is exerted by the laser beam, I can kind of estimate from the equilibrium distribution predicted by Boltzmann, and I can kind of verify that. This is an experimental data. You see that it perfectly fits. Similar thing with kind of, if you have a well that is a circular well that has only walls, so the particles are free to move inside but not go beyond the walls, right? If I put Brownian particles here, the distribution of these particles will be totally flat, because there is no force acting on the particle. There is no reason why a particle will be more likely to be here than there, right? But what happens is that if the particles are microswimmers, depending on their velocity, what will happen is that they will eventually, since they have a swimming behavior, I swim all the way until I hit a wall, right? What happens then? I kind of slide along the wall, keep swimming until I rotate the other way due to the rotational diffusion. What will happen eventually is that as I increase the velocity, the particles will spend a lot more time in the boundaries than in the center. This is due to their swimming motion. Is this clear? So there is kind of a breakdown of equilibrium thermodynamics here. It's more fundamental than just a distribution.
But this is given that the area is not too large, right?
Yes.
Yes. If we wait a long time,
yes.
We will get this random motion.
That's a very good correction. If I take these wells much larger, so much larger than the characteristic length that these are like swimming without changing their orientation, in that case, we will observe something much more similar to this. So their motion in long time scales or length scales go back to the regular diffusion. But if they are confined in an area that is smaller than this length scale or time scale, this thermodynamic equilibrium or the Boltzmann distribution methods won't work for these particles. Well, here is another kind of simulation results for these kind of particles in a harmonic trap. Also, this can be used, for example, these kind of asymmetries can be used to use these particles as a kind of way to transfer from one place to another. What people did is that they kind of created these asymmetric environments, asymmetric barriers. What happens is that if this particle is a microswimmer, it's more likely to climb this side less steep than the other one. So it's eventually it will be transferred in this, it will be more likely to go this direction than the other, which a thermal particle doesn't have this kind of preference. Because if it is this thermal energy, it's only related to the energy of this transition point. But for microswimmers, it makes a difference. By creating this asymmetry, I can actually make these particles go more likely to pass to one side than the other. Of course, people numerically also experimentally have designed different kinds of shapes that are enabling them to kind of trap these particles. Here, for example, you see rod-shaped microparticles that are swimming inside the environment, and they're kind of introducing this kind of V-shaped obstacle. Depending on the angle of this obstacle, what will happen if the angle is small, it reaches to a certain level that all these particles get trapped. What happens is that they all swim along this internal like walls inside on this side, on the right side of this V-shaped obstacle, and they will eventually get trapped. And then once they trap, there is more particle coming from the back and back and back. You kind of create this kind of complete trapping. And if you have a different kind of angle, you can have partial trapping, just because due to the limited area. Yes. 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 I think I have some slides showing that as well. But yeah, you could also use this, for example, to sort microscopic swimmers with certain chirality. Okay, so now we will introduce what happens if we have many microswimmers inside this is what the lecture is about. And what happens is that when inside the liquid environment, there are many microswimmers that are interacting with each other. These particles also may have a phoretic interaction or an aligning interaction. What is a phoretic interaction? Phoretic interaction is essentially a attractive interaction between these particles. So when they come close, they kind of propel, they kind of pull each other to each other. So you see here that this is an experimental result that was actually a very like a seminal result at the time. This is what gives the chapter its name, living crystals. And these are light activated colloids. You see here that they kind of swim into each other, and when they bump into each other, they kind of stick. What happens is that these kind of, as time elapses, they kind of create this kind of crystal structure that is growing over time. And also these are numerically modeled, such motion of these particles. A former master student here, this was published a few years ago. This is not a very old article, you can see here, is that if these particles, microswimmers, have some kind of aligning interactions, they may kind of create small clusters depending on the parameters of the system, or larger clusters, and you can kind of calculate what are the probabilities of having a lifetime of a certain size cluster. And you can see here that, for example, here, what is changing here is that there is a lot of rotational diffusion here. There is less and less rotational diffusion here. And when we have a very high rotational diffusion, particles can barely move. As I decrease it, there is still decent rotational diffusion here, but the particles can still kind of are able to propel themselves in one direction. And here, the rotational diffusion is very minimal. And you see that the clusters, once they are formed, they're a lot more stable. So this kind of interesting behavior can be simulated. And you can actually see, I don't think I'm going to mention that here, but you can see on GitHub, there is an animation code that you can play with yourself, play with the parameters, number of particles, or the number of what is the alignment interaction strength is going to be, or what is the phoretic interaction strength going to be. And you can see how these kind of things work. And you can also see that one. I don't think I have slides, so I can maybe show you. I didn't need to take it here. Take the animation window. What you are going to observe is that if you have a few of these active particles placed inside the crowded environment of passive particles, you will observe that these particles will generate channels. and kind of move along these channels and kind of follow each other within these channels. This is a very common example of how bacteria kind of move in crowded environments. So that this is kind of also could be used to simulate systems like this. Here, what you see as the blue particles are just, or the green particles here are just Brownian particles. They do nothing by diffusing around and bumping into each other. Of course, there is the volume exclusion. When we are simulating these particles, at each time step, we have to correct. This is a little bit tricky because when we have a lot of particles like this, at each time step, we have to correct at the end of the time step that we are kind of extracting, like moving the particles enough that are overlapping away from each other, that no particle is actually going over the other particle. It's a simple kind of rigid body volume exclusion, but we have to implement it. And I take this one away. Yes, and I go back here. Is this clear so far? Yeah. And also, of course, we can kind of come up with more complicated structures. For example, this is an experimental setup that you can see here. They use a lot of these kind of V brackets. What happens is that particles or microswimmers can actually easily, if they swim on this wall, they can kind of follow the wall and get to the other side. But if they hit the wall on the other side, they kind of get trapped inside this V bracket and rotated back into the environment. What happens is that you put many microswimmers in this kind of a room or the compartment of this microscopic structure that is kind of engineered in a way that over time the microswimmers actually are going to migrate to the right side. This is nothing they kind of make them go there directly, but the asymmetry in the systems make microswimmers naturally go easier transition one way or than the other, which eventually creates this kind of asymmetric accumulation. These kind of techniques have been really explored by the scientists to kind of use this kind of activity inside microscopic environments to create useful work, because this is very important for example, targeted delivery or drug delivery inside a microscopic environment, or if you want to kind of operate in a kind of very small environment to make something good, especially biologically. And here also you see that people have exploited also this kind of asymmetric barrier idea to make these kind of experimental structures on a 2D surface. What happens is that you can design structures in a way that kind of will push the particles, active particles, effectively inside, because the asymmetric barriers are designed such a way that they go more likely one way than the other. They go, in this case, more likely to inside. And here they are designed the opposite way. Kind of the barriers are designed the opposite way. What happens is that eventually they are going to get out from these kind of obstacle structures over time. And also these similar structures can be used to kind of sort these kind of particles by their activity. For example, if you have this is a system that is not two-dimensional in a sense that we are not looking at horizontal like a two-dimensional system from up. We are looking at a system from the side. So there is gravity downwards. What happens is that if I release a Brownian particle, it will kind of fall down over time. It still has this Brownian motion, but it's not very strong. What happens is that if I design these kind of obstacle structures, the particle will eventually fall down, right? But it will not have a certain direction. But obstacles are designed such a way that if it has kind of a swimming ability, that is, it's propelling itself in one direction, it is kind of following these kind of patterns. It's falling at different angles. And you observe that if the particle is more and more active, it is kind of effective motion downwards. Its angle is changing depending on the activity of the particle. So this kind of a system can be used to kind of sort particles in terms of different activity, swimming velocity, I mean, by activity. And also this kind of what is called called a chiral flower by, yeah, he was a master student also a lot of years ago, a little bit actually before me. But yeah, Mita has made these kind of simulations where you can kind of demonstrate that you can also sort them by chirality. If you think about it, if I have a particle that is left chiral here, like swimming like this, it is very unlikely that this particle will swim out of this. But if I have a particle that have right chirality, these asymmetric obstacles are designed in such a way that they are very easy to get out in one of these holes, right? The same with the other one, just the opposite. If I have a right chirality, it is for me very easy to get in here, but it is very easy if I'm swimming like this. It is very easy, very difficult to get out once I am inside. And this can be shown that here maybe it's not the projector quality is not very good, but you have two types of particles here, red and black, and you can later see on YouTube, or you can go and find the paper and download yourself the original video. But you see that over time, there will be only one kind of chirality that is accumulated on one side and another kind of chirality that is accumulated on the other side. These kind of structures. These are very like novel ideas to use these kind of asymmetries for microscopic particles to kind of sort them or make them do some useful work in a microscopic environment. So yeah, I have mentioned a lot of different things, but most of them actually based on the principle of this motion of microswimmer particles that are the active Brownian particles that differentiate from the original Brownian particles by their swimming motion. Okay, that is the key takeaway. And their motion in short time scales or length scales create this kind of super diffusive behavior. Okay, and this is not like the regular Brownian particles. You cannot apply any of these techniques to a regular Brownian particle that's not swimming. You cannot differentiate them if they are diffusing more or less, for example. You cannot make these kind of different obstacles and one type of particles for one size, for example, or less diffusional coefficient will accumulate here and particles with more diffusional coefficient accumulate on that side. You cannot just do it the same way that we apply these techniques on microswimmers. Is this clear? Yeah. And there is a very nice review articles that is called Active Particles in Complex and Crowded Environments. It is listed in the additional readings section of this lecture on syllabus. So you can go to that article if you're interested in more of these things. What else has been done? It's a very, very nice review paper that you can go and read. Any questions? Everything clear with this chapter? Okay, I think at this point we can take a break unless there is a question in the chat. There was a question. What is the W term in the orientation term? That term is not in the notebook. Yes, in the notebook, the GitHub, I think Wesley is mentioning in the chat of the Zoom is that this chirality term here. I need to go back there. This term here, W, is only, I can maybe show it here, it's easier. This term here is only there if the particles have chirality, and you can introduce it. But the ones that are, the codes that we have on GitHub is about crystal formation and channel formation of these microswimmers. And there the particles don't really have chirality. But of course, you are free to add it and try to see what happens. Okay, so this is kind of that term is creating this kind of asymmetric propulsion that the particle is going over time in kind of not only propel itself, but kind of also rotating in one direction or the other because of the asymmetry. Okay, so it's coming from the propulsion of the particle, but the configuration is somewhat asymmetric, that it's not only applying a force on itself that is propelling, but is also applying a torque on itself, which is kind of creates this kind of angular motion in over time. So it's kind of turning around. Okay, everything clear? We did not define rotational diffusion, but I think it is defined in the lecture notes. But what we said importantly is that yes, it does have units. It has to have units, but so that I'm actually now not sure that it has units, because the diffusion coefficient has units because we have to still multiply it by time, right? And it's giving us an angle that doesn't have units, because this has radians that doesn't have any units, and diffusion coefficient multiplied by time, we can see that in the next one here. This has no units, right? It's angle. It has radians. And this has to have units. Of course, the random number doesn't have any units. It has to have the units of 1 divided by seconds to match the units, because it should not have the overall, the inside the square root, it should not have units. And this, of course, is term is proportional to the temperature and inversely proportional to the cube of the particle radius. And I might assume that it is, oops, let's see here. Actually, no, we don't maybe mention the full expression, but it is, I don't remember, 8 kBt divided by r cubed. It is kBt on the numerator and divided by r cubed in the denominator. Sorry? Or 8 kBt divided by pi r cubed could be. I don't know, Google it. But I tell you, it's kBt on the denominator and then r cubed. I don't know. It was just a question. You can Google it. But I think it's r cubed. Yeah. But importantly, it scales with, how do I go back now? It scales with temperature divided by r cubed. You just need to take, I mean, if you want to model it with a certain particle size, then when you change the size, the diffusion coefficient is changing like this. And it's different from the translational diffusion. And if you want to just take parameters, which in this lecture, we focused on just assigning a rotational diffusion coefficient ourselves manually to a particle. So kind of we give a rotational diffusion coefficient and change it to see what happens. Okay? I am not sure, but I just quickly looked at it. I didn't see it. But anyway, yeah, we can take a break and come back in 15 minutes. Ah, yes, maybe we can talk at the end of next lecture. We can discuss. Okay. The next Thursday, which is supposed to be the correction day for homework 4, is likely to be postponed. Yeah. Okay.
The problem is that we don't know yet if there are classroom work to do it. So we cannot do it next week. It will be on the 9th. That's for sure. We will let you know where. There is a, if you don't get any classroom work, there was it. Okay. But I strongly advise you that you don't wait until the 9th for the next. Try to do it still by on the original schedule, because the last 2 weeks should be really dedicated to the project, not to the. So don't wait until the. So it will
be available on Friday.
On Friday, you can still book the time. I will be on the 9th. But you have 2 weeks. But my advice is that you don't spend 2 weeks on the honor. And try to finish it on stage so that you can then focus on the project for the course and the presentation. But the problem, the essential problem is that on the second, you would have had only 2 people to correct, which is not enough to be sure that we understand everything.
Okay, so we continue in 15 minutes with the next chapter. Let's see now.